In this section, we're going to take a closer look at limits in terms of actual functions instead of as we looked at them in 2.1, which was dealing with velocity. For the time being, we're going to use this informal definition that says if a function becomes arbitrarily close to a single real number, we're going to call that L, as x approaches a value a from either side, the limit of that function is going to equal L. So a whole lot of math words gets kind of confusing. So here I have this graph of f of x. And as I approach this single value a, so I'm looking here when x is a, I look as I come from the left and as I come from the right, since they're approaching the same y value, which we're calling L, as we approach that a value from both sides, that's how we know that that's what the limit is reaching. Okay, we have three ways that we can find limits. We can do it graphically by drawing the graph by hand or using technology and looking at what's happening as we approach that a value and see where it's going. We can use the numerical approach, which is constructing a table of values, much like we did with finding our instantaneous velocity. And we can use an analytical approach, which means we're going to be using algebra or calculus. Okay, so we're starting with the function f of x equals x to the third minus 1 over x minus 1, where x doesn't equal 1, because if I plug in 1, I'm going to have a 0 in the denominator, it's going to be undefined. So I want to find the limit as x approaches 1 of f of x. So what's happening to this graph as I get closer and closer to 1? Well, I just said if it happens that we substitute 1 in for x, we get 0 in the denominator, it becomes undefined. And that doesn't really help us figure out what the value of the limit's going to be. So since substituting it in isn't helpful, we want to actually take a look at the graph. So we have f of x equals x cubed minus 1 over x minus 1, where x doesn't equal 1. To figure out what this graph looks like, the first thing I do is I factor my numerator, which is a difference of 2 cubed, so it factored to x minus 1, x squared plus x plus 1 over the x minus 1. My x minus 1 terms simplify to 1, so that tells me that this graph is equivalent to the graph of f of x equals x squared plus x plus 1, which is just a parabola, except there's a hole at x equals 1. So that means we know f of x is not defined when x equals negative 1. So looking at this same graph, in order to figure out the limit, we need to be approaching that 1 mark as we go from the left and from the right. So in order to find the limit, I'm going to look at the limit from both sides and make sure they equal each other. So I'm starting with from the left. I want to know what's the limit as x approaches 1, and that's what this negative sign up here is telling me, that it's coming from the left of f of x. So as I'm following this curve, and I'm coming down and I'm getting closer and closer and closer to 1 as I come through, my graph is approaching 3. So then I look at the other side. I want to know as x approaches 1 from the right, so that's the 1 to the plus. So now I'm coming in this way, and these values are getting closer and closer to 3. So since we're approaching the same specific value from both sides, we know that number is 3. That's going to tell me that my limit of this function at that value is going to equal 3. Now we can do the exact same problem, but we can do it using a numerical approach and making a table to see what's happening. Instead of graphing it through, I can start with f of x equals x cubed minus 1 over x minus 1. I don't have to think about simplifying it, seeing that there's a hole. I'm going to start from the left, so values smaller than 1. And I'm going to keep getting them closer and closer to 1, and I just plug in my values, and I see what's happening as I get there. Then I have to go from the right. So I'm going values greater than 1, and I'm getting closer and closer to 1. I'm decreasing my values, and I watch what's happening. So 2.313, 2.710, 2.970, 2.997. Coming in from the other direction, we were at 3.813, 3.3310, 3.03, 3.003. So the question is, what's happening right in between? Well, if I kept going closer and closer and closer, we can see that these values are getting closer and closer. So we know that they are approaching 3 from both sides. So the limit as x approaches 1 of f of x is equal to 3. So we've done it graphically, we've done it numerically. Now one thing to note is that limits are independent of it being a single point. We're going to talk more about that in just a minute, but make sure we pay attention to that one. So when we did this numerically, we were using what we call one-sided limits. We were looking at it as it approached from the right, we were looking at it as x approached from the left. So again, this is just our notation, As x approaches a number with a positive, it means it's coming from the right. As it approaches a to the negative, that means it's coming from the left. So we want to make sure we're familiar with that notation. So when we're finding that limit of the function, we're going to let x approach a from both the left and the right, and as long as it's the same value of L that's being approached by the function from both sides, our limit exists, and we can say the limit as x approaches a, notice no plus or minus because it's approaching it from either direction, that f of x, that limit will equal L. Okay, so looking at another one numerically, we said finding the limits as x approaches 2 of x squared minus 3x plus 2 all over x minus 2. So again, as I want to go as 2 coming from the left, so I went 1.75, 1.9, 1.99, 1.999, so I'm getting closer and closer to 2 from the left. And then I need to look from the right, so I started at 2.25, decreased, got closer, 2.1, 2.01, 2.001. And as I evaluated those, so I plugged in my values, I had 0.75, 0.9, 0.99, 0.999. We skipped 2, we weren't sure what that was because we know immediately at 2 it's going to be undefined. And then 1.001, 1.01, 1.11, 1.25. So we can see from this that as we're getting closer and closer to 2, we're skipping over the number 1. So this is approaching 1. Okay, we can also look at these again graphically. So if I have a piecewise function, a graph that's not continuous, one part is one graph, one part's another graph, I can do the same thing. So I'm looking at when x is equal to 1 of h of x. So I need to know what is the limit as x approaches 1 from the right. Well, if I'm looking at just from the right, following this, the closer and closer I get to 1, the graph is approaching 4. I also have to look at the limit as x approaches 1 from the right. And looking there, I'm coming down here, and now my graph is approaching negative 2. Oops, sorry, bad notation. This is h of x. The limit of h of x, I can't just write limit. I have to write the limit of what I'm taking the limit of. So the limit of h of x as x approaches 1 from the left is 4. The limit of h of x as x approaches 1 from the right is negative 2. Well, 4 doesn't equal negative 2, so we say that this limit does not exist. And a lot of times instead of writing that out, we will write DNE for does not exist. The limit does not exist. Now sometimes what people use or they refer to is called the wall method, and it's just a visualization to help us better see that the graph is going to 2 different places as we approach 1 point. And we can see that here using that wall. This blue line represents the wall, and these 2 graphs are not hitting the wall in the same spot, so my limit does not exist. All right, so here we have another piecewise function. F of x equals 1 when x doesn't equal 2, and f of x equals 0 when x does equal 2. We want to find the limit as x approaches 2. Now, if we were to sketch this piecewise function, x equals 1 as long as x doesn't equal 2. So it's going to get really, really close. It's not going to hit here. And for every other x value, this is my graph, but at x equals 2, the point is actually here. So when I want to evaluate my limit, I'm going to start with the limit as x approaches 2 from the left of f of x. So that means I'm following along the line right here, and I can see that it is approaching 2. Okay? As I go from the right, the limit as x approaches 2 from the right of f of x. So I'm following the graph, following the graph, following the graph. It's getting really, really close. It's approaching 2. So this tells me that my limit here, since from the left and from the right are equal, my limit here is actually equal to 2. So the limit as x approaches 2 of f of x equals 2. But now notice that's not what's happening on the graph. When x is 2 on the graph, the function is equal to 0. So this is a great explanation of what we mean when we say that limits are not affected by a single point. We have to be looking at the grand scheme of the picture, not just exactly what's happening at that x equals 2. We're looking at the actual graph, right? We came in from the right, we came in from the left, and those 2 sides are approaching that same value. It is independent of what the graph itself actually does, what the function is doing. We're looking at the whole picture. Okay, so here we have another one. So we're going to talk about limits that fail to exist. I have f of x equals the absolute value of x divided by x. So if I take that absolute value and I break it apart and I rewrite it as a piecewise function, it's actually equal to the function f of x equals 1 if x is greater than 0 and negative 1 when x is less than 0. So we can see here's my graph. There's the negative 1, there's the 1. Now this graph, just the picture, mind me, is not great. They both say less than, so these should be open circles. These are not closed circles on my graph. So my limit as I'm coming in from the left to 0 is hitting negative 1. The limit as I'm coming in from the right is hitting positive 1. Since these aren't equal, the limit doesn't exist. So my two-sided, my full limit does not exist. They have to be coming to the same spot. Okay, so to summarize, the limits that won't exist, the first one is when f of x approaches two different numbers as I come in from the right and I come in from the left, and that's what we just saw in the last two examples. F of x, if it's increasing or decreasing without outbound as x approaches a, means it is not going to exist. So for example, if I have a graph and the graph's just going bigger and bigger and bigger, the closer I get to 3, meaning I have a vertical asymptote there, the limit doesn't exist because there's no limit to this, it's just getting bigger and bigger and bigger. And then the third is if f of x oscillates as x approaches a. So if it's going back and forth, and it's just constantly going back and forth, we don't have a limit. All right, so let's practice again reading a graph, make sure we have this down. So I'm giving you this function that's graphed, we're calling it t of x. First question asks, find the limit of t of x as x approaches 4. Well, over here is x equals 4, and I need to approach from the left, and from the right, we can see it's approaching the same value, so this is equal to 2. Right? The second one, limit of t of x as x approaches negative 3. So here's my negative 3 mark, and I'm following the graph. So from the right side, it's approaching 3. From the left side, it's approaching 3. Now notice the function there, t of x of negative 3, so t of negative 3 is actually equal to 8, but that's not what the limit is telling us. The limit is telling us is what's happening as I come in from the left and the right, where are we approaching? Number 3, the limit of t of x as x approaches 0. Well, here's 0. As I come from the left and as I come from the right, this is going without bound. This limit does not exist. The limit as x approaches negative 6, so that's kind of the end of the graph over here. So even though it's only coming in from one side, since that's the end, that's an endpoint, we can say that that limit is actually 3. The limit of t of x as x approaches 2, so here's x equals 2. As I come in from the left, I hit 3. As I come in from the right, I hit 2, so this limit does not exist. And our last one, the limit of t of x as x approaches 5 is right here. So coming in from the left, we're at 2. Coming in from the right, we're approaching 2. This limit does exist, and it's equal to 2. Okay, so we also kind of want to be able to think about this in reverse to make sure we truly are understanding what's happening. So we want to sketch a graph with this criteria. The domain of the function is negative 2 to 3. The range is 1 to 5 uninclusive. The limit of f of x as x approaches 0 does not exist. Okay, so that means we're going to get close to 1, but we're not going to hit there. So I'm going to start by just sketching an xy plane. I know I'm going from negative 2, inclusive, to 3, but that's not going to be included, so it means it's going to be an open circle. And my range is going from 1 up to 5. And as I approach 0, I know, sorry, this didn't type too well for some reason, the limit as x approaches 0 of f of x does not exist. So we have a few things. So that means as I'm coming into that y-axis from either side, they can't be going to the same place. So I'm going to say, I don't know, maybe I have an open circle at 5 because the range gets close to it but never touches it. And I'm going to say I start at negative 2, maybe at negative 2, 2, and my graph goes up. Okay, so that meets my criteria. And then for 5 over, I'm going to say the graph here is 1, and at 3 it goes up to 2. So this meets my criteria because as I go from the left and the right and approach 0, I'm not hitting the same value, so my limit doesn't exist. I'm going to have an open circle over here at 3 because it's not included, and I have open circles here but a closed circle. So there are lots of different ways we could sketch this. This is just one possibility, something you want to make sure you're thinking about as you're dealing with limits.